Good afternoon all. Firstly, just thanks Boris and WoodSolutions for having us along. It's great to be here, and it's great to be amongst sort of peers in the industry to discuss mass timber, particularly where it's going or where it's come from and very quickly is going. So yeah, thanks again. I guess whilst some of the other presenters here today were providing a bit of a holistic background to some of the testing and how we got to the prescriptive changes in the BCA or NCC 2016. Today, Rob and I are looking to primarily discuss where the industry is quickly going, particularly with a lot of design teams and designers wanting to pursue exposure of mass timber and pushing the bounds of mid-rise into the high-rise realm. I guess just what we're going to be taking you through. So I guess just again, and I'll skip over parts of this that have already been touched on, but again, just the elements of the mass timber that we're talking about. Performance-based design and where it sits within the NCC. I think we've seen the image a few times already. Then looking at a risk-based framework, and a little bit of this ties back into with what Paul's already discussed, but it just takes it just a little bit further. And then I'll pass over to Rob, who will delve, I guess, a little bit further into some of these technical challenges and what we're seeing with all the current research that's coming out from, I guess, academics and being published and altered to varying extents in other building codes around the globe. So, again, just touching on, I guess, what we mean. So, again, we're talking about basically things, mass timber or heavy timber, also engineered timber, as it's called in various parts, but primarily from the performance aspect of this mid and high-rise construction that we're about today. We're looking at glulam, CLT, and LVL construction. And then again, just to make sure, today we're wanting to focus, I guess, more on the mass timber rather than this stick frame construction, which again has already been introduced and probably is more at around the 1 to 6 story mark or minor extensions and tack-ons, whereas we're talking about the solid construction and particularly, I guess, in what we're looking at is where it fits in with what teams are looking at in terms of 2s and 3s, but also 5s and now even vertical schools and education facilities, so similar buildings to this. So from there, where we're going is, again, the same slide that we've already seen. So we're now talking about the other side. We're talking about the performance aspects of it, and particularly with this exposure, and how we can consider the relevant parts and technical issues that we need to define. So I guess what Boris was looking at and noting, and with these NCC prescriptions, we're dealing with some of these issues from a passive, notably from a passive and an active combined system, and now this is looking at how it performs in natural fires and some of these issues that we need to take into account. So, just got to find where I am now. So again, in terms of this performance side of things, we're looking at designing to a targeted level of performance, so in accordance with these performance requirements. And often in order to do this, what we're needing to do, so from, I guess, based on most of the audience who we see here, most people are across this from a fire engineered and performance perspective. We're needing to develop a fire engineering brief about the proposed methodology we're looking to utilise, develop up that strategy, present it to the design team and the fire authorities in order to allow that to be scrutinised if so desired or challenged, and making sure that we're holding it to the right accord. And then beyond that, we're taking it forward to a fire engineering report and fully assessing the issues, in this instance, the exposure of the timber, and developing that to an extent which the building surveyor would then use as part of issuing the main building permit. So again, what we're seeing from working in the field is now hand in hand with these prescriptive changes that have come about from 2016, is we're now seeing a lot of these design teams now start to say, well, if we've got all these benefits associated with mostly cost, but also just trying to get the speed of construction up and going, then why don't we now try and look to expose this timber and get some of the benefits, again, that Paul touched on briefly at the start, and basically about, well, now let's look at the wellness aspects. Let's look at just how people look and feel in the whilst residing in these buildings. And there's also some recent evidence to show that it can now, particularly in office buildings, look at higher rental yields. So developers are starting to sort of say, oh geez, that's something we might like to look at. So now, I guess, in terms of how it ties in with the performance requirements, and I guess what we see and how we're seeing it, and from low-rise through mid-rise and high-rise. So again, from a bit of a risk-based methodology, we're seeing that it's quite readily accepted that your low-rise buildings, from a performance side of things, can be lost in fire. So we see it nationally on the news quite regularly that 1 to 3 story buildings, they're burning down, the fire brigades are attending, and normally everyone's getting out okay, which is typically accepted from the community as well. Now when we move into the mid-rise construction, we're now seeing that, as Paul touched on, we've got more occupants in the building, and we're now seeing that we need to have consideration of either that there's been enough time for sufficient, for all occupants to escape. There's been a demonstrated period for fire brigade intervention, and typically that's got a large factor of safety on as well. So that's either from a prescriptive viewpoint or from a performance aspect. So that's meeting the deemed to satisfy FRLs, or if we're looking at a performance-based assessment, we're demonstrating how that's achieved. So then I guess where we've moved to is when we're pushing towards the upper mid-rise and high-rise developments. Now we're looking at a lot more buildings, a lot more occupants within the building. They might be in the building for a long period of time. It depends on how the cascading of the evacuation might work. There could be occupants above the fire floor, and the fire brigade about how long it takes them to arrive on site and intervene. So in this aspect, and again, this is how we are interpreting exposed mass timber, particularly on the mid and high-rise developments now, on the upper end of mid and mostly high-rise, is that structure in that fire compartment of origin, it needs to demonstrate that it's survived the burnout. Now it's a bit of a topical item, and a lot of people say, well, actually the performance requirements don't actually state that, but we see that that's something that probably needs to be discussed and reviewed a bit more from the industry, and particularly noted with respect to mass timber. So if we move over into going back to a risk framework, so everything we do as fire engineers is comes back to risk. Commonly adopted risk framework methodology is looking at the probability of an event occurring times the expected loss in the case of the incident or the consequence. So in terms of looking at this for taller developments, the probability of the incident starting is, and again, something else that Paul did touch on as well, so we've got a lot of commonalities here. It is increasing. We've got a larger building, more floors, so therefore the probability of that occurring in the first instance is increasing. But then we've also increasing it with the consequence. We're looking at if the incident occurs, this also substantially increases with respect to the damage that might occur. And so whether it's a community expectation now about whether that mid to upper and high-rise building needs to retain in place, particularly when we have fire brigade coming in and intervening in such buildings. So I guess when it's a bit of an advert for Lemley Centre with a couple of their buildings up there unintentionally, but the only one we've got slightly out is this should have been greater than 25 metres for the Forte building. But we just tried to put this in a bit of a perspective of risk versus time, and mostly from a perspective of, in the last 5-6 years, we're now starting to see these, again, I come back to this, on the fringe of mid to high-rise buildings. So we're going from this period of where we had a completely encapsulated timber building, fantastic piece of for the timber industry in Melbourne, and then there's been a few other developments around town, but then what we're talking about is particularly now with some of these mass timber office buildings that are coming about, and the appetite, I guess, for exposure of these elements, that we're now starting to see, well, we were under 25 and now we're moving up to an over 25 metre building, and what the implications of that specifically are for dealing with, again, I come back to those points of the height, the exposure, the use of the building, the time for evacuation, and the number of occupants. So I guess what we're trying to highlight through this is we're trying to say, with the speed and time that these developments are occurring from a performance aspect, as fire engineers, we need to be quite cautious, and as designers, that we're adequately addressing the risk that comes along with this. So I guess, yeah, the whole purpose, and I'll pass mostly on to Rob to delve really into these technical issues about the research that's out in the market. We're just trying to make sure that the designers, all fire engineers and approval authorities are across some of these key knowns and unknown issues about where some of the limitations in some of this research is at the moment, and where still needs a bit further work through either additional testing or additional involvement with research institutions. So pass over to Rob to keep things going.
Okay, thanks, Trav. Afternoon, everyone. So, as Trav said, I'm just going to touch on some of the main technical challenges that are brought about by exposing timber, particularly in taller buildings. These are the main things as we see at a fairly high level. They're all interconnected, so I'll just go through them now. So the first one's fire resistance levels of buildings. There's a push actually, kind of counterintuitively, to reduce fire resistance levels for exposed mass timber buildings. And this is understandable really from the developer's point of view, because where you're exposing mass timber, the section size is actually the protection of the timber. So if you reduce the fire resistance level, you're reducing section sizes, and also it allows you to use sort of off-the-shelf tested connection systems, for example. So there's a fair few systems out there for 90 minutes. There's not too many out there for 120 minutes. So I think there's a bit of pressure on fire engineers to reduce the fire resistance rating. But on a most basic level, if you're exposing the structure, you're actually adding fire load into the building. So I guess the fundamental question is it reasonable to add fire load in and remove fire resistance? And for some buildings, low rise, low risk, potentially that may be reasonable. But for taller buildings that everybody's been talking about, Paul and Travis have been talking about, where people can be trapped above, and you're talking about the buildings having to survive the full burnout period plus some extra where the structure burns afterwards, then I would say this is not a reasonable approach. The main difference is obviously the structure is fuel, it contributes to the fire. So just to illustrate how much, I've included an excerpt from Xiao Li's paper from Carleton University in Canada, and this is basically a room test, and the green line, the light green line, that is basically a fully protected room. So this is really the heat release from the furniture against time. So you can see it burns and then decays. So the pink line is fully unprotected, so completely exposed CLT around. And you can see a number of interesting things. Obviously the peak energy release is a lot higher, but the most important thing really is the duration of burn is a lot longer, and you see another peak in heat release rate spike there. And just to kind of think about this in terms of the code or something like that, let's say if this is a 60-minute building, you can see with a protected building, you die it out, you probably survive your 60-minute FRL period. But with the exposed timber, after 60 minutes, you're up at 6 megawatt fire. It's a big fire. It's unlikely that's going to survive the FRL period. Fire resistance levels, the basic equation is the more timber you expose, the more fuel you've got, the longer the duration of fire, which requires increased fire resistance levels rather than decreased. Just to put this in the context of some fire modelling, this is based on some test data from Canada. The red line is a parametric kind of fire that envelopes the test results. And we've got a typical compartment over here, 500 megajoules per meter squared. And so this red line is the temperature time profile for a fire in there. Dog got out, by the way, don't worry about that. He's not part of the fire load. So, but if we increase a bit of the timber, so if it's an exposed timber roof, ceiling, you can see that there's more energy release. The temperature stays higher for longer. And then again, if we have a fully exposed timber ceiling, you can see the decay period, rather than starting to decay here, is decaying right over here. So it's a clear illustration that the more timber is exposed, the longer your fire and the more fire resistance you need. In terms of structural engineering for timber buildings, fire resistance, very simple concept. Char rate times exposure time. But as Paul's touched on, it's quite complex in practice. So what is the exposure time? Again, it's going to be building specific for a tall building, the complete burnout of the building, including the time for the structure to burn as well, if there's any exposed. And burn duration increases with the amount of exposed timber, as we've seen. So the other side of that equation, what's the char rate? There's very simplistic char rate calculations you can do, but they're not always applicable. They're not really applicable to CLT. I know that the Euro codes are being modified so it can be used with CLT. It's building specific, so in terms of fire compartment size, fuel load, ventilation, so it's basically related to the intensity of the fire, which Paul touched upon. It's timber specific, so different timbers char at different rates, different types of timbers char in different ways, so, and it's exposure specific as well, so in terms of the time, but also the location within the compartment. There'll be hotspots within compartments where, for example, you've got two exposed timber surfaces coming together and they can re-radiate in between. You get much more accelerated char rate there. The next thing is self-extinguishment. This is a big topic for timber fire engineers. Everyone's talking about it. So basically, self-extinguishment is defined as if you take away the heat source, then at what heat flux does the timber cease to burn? So it's a really influential factor in designing timbers, exposed timber buildings. So for this we use a simplistic model. This is from Roy Creelard's paper from University of Delft in Holland. So we have unprotected timber, unprotected CLT, sorry, we have a fire in the compartment, the CLT flames, the fire flames, the compartment fire dies out, this continues to flame and it transitions to smouldering, the timber that is, and then that transitions to self-extinguishment. But given it's such an important factor, you know, what do you use as your self-extinguishment criteria? It's really important to get this right, otherwise you could significantly underestimate your fire resistance period. So there's a bit of debate in the academic communities about what to use. University of Queensland did some a really good experiment where they specifically set out to demonstrate that that self-extinguishment can occur, and they did that, and they did it by putting the perfect ventilation characteristics, the perfect airflow across the exposed surface, a really low fire load, and they managed to demonstrate that you could get self-extinguishment at 45 kilowatts per meter squared, which is a pretty high incident heat flux. But and they were coming from a research point of view. That was their baseline experiment, so as that from there they could then vary the parameters to understand what influences self-extinguishment. They clearly state this should not be used for building design. It's not representative of a building at all, and they're actually looking for funding to do some more building representative full-scale models. I mentioned Roy Creelard from Delft University. He did some separate experiments, and he showed that self-extinguishment occurs around about 6 kilowatts per meter squared. And basically he defined self-extinguishment as the transition from smouldering to out, whereas University of Queensland, they defined it as the transition from flaming to smouldering. Now in terms of building design, particularly for exposed structure, you know, if your timber's still smouldering, it's still burning, you know, you're still losing fire resistance out of your building. So we would much prefer to see self-extinguishment limits in this region. And what's the impact of that? I mean, it's a huge impact. If you have a fire here and you say, you know, anywhere outside of 45 kilowatts per meter squared ceases burning, then you'll get a fairly small area of impact. Whereas if you extend that to 6 kilowatts per meter squared, you get a much larger burn area, much larger burn duration, and it has a serious effect on the fire dynamics within the compartment. It can re-radiate down to furniture over there and cause a travelling fire. Then you can get a big fire. And so I think for design, for performance-based design, if you're using test data to validate your design, then you definitely need to demonstrate how compatible the test is to what's going to be in your building, the configuration. Delamination, the next technical challenge, which we've touched on before. This, I think, is currently the Achilles heel for CLT in fire. Basically, most of you probably know, CLT is a layered product, and delamination is where the fire burns through the bottom layer, glue melts, and the bottom layer falls off. It exposes fresh timber, and a few things happen which aren't great for fire resistance. You get it because you've got fresh timber exposed and you've got some fall off. The intensity of the fire grows. You'll get a spike in char rate, which means you're actually losing fire resistance faster, and it inhibits self-extinguishment, so it can lead to regrowth and very unpredictable fire dynamics. And if you get regrowth, obviously your duration increases, your char rate increases, and your fire resistance level needs to be a lot higher. And this was demonstrated in the Fire Protection Research Foundation test. So this is a room test again, one wall, exposed CLT. So at 157, the fire's almost dying out. 10 minutes later, delamination's occurring and it's growing. 7 minutes after that, you've got a fairly intense fire again. So this is a good demonstration that regrowth can occur. And in this situation, you've got a pretty intense fire in there, and you've actually lost at least one layer of protection. So adhesives, the choice of adhesive is absolutely fundamental in the performance of CLT, the fire performance of CLT. So high temperature adhesives can actually reduce or completely eliminate delamination, which, as you can see, will really help us as engineers to justify more exposed timber within buildings, to safely justify it, just because the char in the fire dynamics is a lot more predictable and it's just a lot more fire resistant. So to illustrate that, this is a excerpt from a paper from ETF in Switzerland, who are like world leaders in timber fire research. They tested 2 CLT samples, both with PUR glue, so not even the formaldehyde glue, but this was a high temperature adhesive, and you can see that the char rate through the high temperature adhesive, it basically behaved like a solid block of timber, so very predictable, very fire resistant, whereas wasn't so good with the standard glue. So if manufacturers out there, I know University of Melbourne are looking at this, and I know XLAM are looking at this, but to get high temperature glue in CLT would be a step change for the industry, I think. Connections, so the weak point of the structure. Any exposed timber connection should undergo a loaded fire test. Connections are difficult, nigh impossible to to determine the fire resistance analytically, so hence full-scale fire tests should be used. Not all connection tests are loaded, which I don't really see as for compatible use in the building. This is some photographs from some connection testing we were involved in the US. So we tested some off-the-shelf connections and then some project-specific connections. These are glue-lam to glue-lam connections. And as you can see, we managed to demonstrate that under loaded tests they achieve 120 minutes. So that's going to be quite a step forward for the industry, because once we can have an exposed timber connection that achieves 120 minutes, then I think there'll be less pressure to reduce fire ratings, and when it's probably not applicable. Encapsulation, so there's lots of good information from WoodSolutions and others about encapsulation. However, if it's not detailed properly and the encapsulation fails, which many fire tests show that incorrectly detailed encapsulation does fail, either by falling off or using the wrong materials, so that char goes through the heat travels through the material. If the timber behind that has not been designed to char, then as soon as that's happening, you're losing structural resistance, which can be a dangerous situation. Encapsulation failure can be used as part of a performance-based design, as part of a system, where you partially rely on the encapsulation, then partially rely on the charring of the wood, but this really needs to be underpinned by compatible test data. You need to be very sure when your encapsulation is likely to fail. some performance-based watch it. So this is basically for other fire engineers or approval authorities or anybody that's involved in a design team for an exposed timber building. So fire testing, fire dynamics has shown that the more exposed timber there is, more fuel, longer fire, higher char rates, and a higher fire resistance required. Delaminating CLT can lead to regrowth, which is unpredictable and again can lead to higher fire resistance requirements. Very adhesive dependent, which has been demonstrated by a number of tests. CLT can only really be designed predictably if it's been shown to not delaminate, so using high temperature glues. Otherwise you have to think of some of the ways to minimize that unpredictability. And as we've touched on, the current UQ tests are not to be used as a basis for building design, as they're not really a realistic situation, and they'll be the first to admit that. So this is WoodSolutions, so a couple of practical design measures, some solutions. So we should definitely consider the amount and location of exposed timber, particularly in the context of the risk of the building. You know, if it's a really tall building, or you know it's a high risk building for whatever reason, for you know egress or whatever, then very carefully consider the amount and location. So want to really avoid large exposed surfaces of CLT. So our modelling and some of the larger fire tests have shown that you get a slightly different flashover mechanism with when you've got exposed surfaces, where you get a localised flashover way ahead of the fire, and that can accelerate fire spread within the compartment. Also, as I touched on before, re-radiating surfaces. You know, if you can avoid two timber surfaces together, then you know, pretty much every test where that's been carried out has shown that the intensity of the fire is greatly increased. And the location of timber, you know, one thing with exposed timber as well is external fire spread, so a fire breaking out and breaking back in. So flame extensions will probably be a lot greater if you've got an exposed ceiling, so you need to design something to prevent those flame extensions breaking back in on multiple layers above. Adhesives we touched on, high temperature adhesives, we can get rid of delamination, and you know, it makes life a lot easier. Not saying you can expose everything, not even most, but you know, some more. A thick lamella of CLT, so on the exposed surface, if you can design in a thick lamella of that, then that maintains predictable fire dynamics for as long as possible. If you've got complete sort of control, if you're right at the beginning of the project, you can configure compartments to have favourable ventilation conditions in terms of compartment size, fire load, and opening size. Any exposed timber at all should be part of a holistic design, such as improved sprinkler reliability, egress systems. So the exposed timber and the structure is a subsystem, basically, that must work in conjunction with a number of other subsystems to ensure the safety of the building in fire. And I think NFPA 550 that Paul talked about is kind of a tool that can help you with your holistic design. And also project-specific testing, so I guess Stephen's going to talk a bit more about that. But yeah, very important for your connections and your penetrations and whatnot to get, if it's not project-specific testing, compatible test data that you can reliably draw on. And I think if we follow some of those guidelines, you know, we can produce some lovely exposed timber buildings. We can design them safely and promote and sustain the future of the timber industry. So, thanks very much.